You know, every massive skyscraper, every bridge, even your own home, they all rest on a foundation that's completely invisible to us. It's this hidden world of soil layers and unknown conditions. So how in the world do engineers actually map this invisible world before they even start building? Well, that's exactly what we're going to break down using the brilliant guide from Indian Standard 1892.
It really is the first and honestly the most critical question of all. Before a single blueprint gets finalized, you have to face this uncertainty head on. What kind of soil are we dealing with? Is there rock down there? Is it even stable? The success of the entire project literally rests on getting this answer right.
And this is where the standard just brilliantly cuts through all the complexity. It boils everything down to two basic questions. First, you've got the XY axis, which is basically the bird's eye view of the site. Where exactly do we look? And second, there's the Z-axis, the cross-section view. How deep do we need to go? Simple as that.
So here's our game plan for this explainer. We're going to follow that exact logic. We'll start by defining the problem. Then we'll tackle the XY axis to figure out where to investigate. After that, we'll get into the golden rule for the Z-axis to see how deep we need to go, check out how that works in the real world, and finally, pull it all together in a super useful tool I'm calling the Investigator's Matrix.
All right, let's get into it. Just remember, we're taking what seems like a complex, three-dimensional geological puzzle, and we're breaking it down into a super manageable two-step process, location and depth. First up, let's talk about the surface plan. So this first part is all about strategy. This isn't just about digging random holes and hoping for the best. It's about being smart and placing our investigation points based on the specific type of project we're working on. Now, for a small site, like a single house, the logic is really clever. Sure, you put one investigation point right in the center, where the main load is going to be. But you also check the corners. Now, why would you do that? Well, you're looking for any sloping or dipping soil layers that could cause some serious stability problems down the line. It's a simple but crucial check.
Okay, so as the site gets bigger, our strategy has to scale right up with it. For these large developments, think big apartment complexes or industrial parks, we switch over to a systematic grid pattern. This makes sure we get full coverage, with boreholes no more than 50 meters apart. The whole point is to create a reliable underground map and avoid any nasty surprises hiding between our test spots. But what happens when we start building up? Well, the risk just changes completely. With high-rise buildings, the loads are absolutely immense, and they're all focused on a small area. So, once a building gets taller than 50 meters, the standard says you need a minimum of 3 boreholes. This isn't just about covering the area, it's about data redundancy, making dead sure our understanding of the ground is rock solid. Now, projects like roads or railways are a whole different ballgame. The investigation has to be adaptable. You see, if you're on nice, uniform ground, you can space your points out, maybe up to 500 meters apart. But the second you hit weird or tricky terrain, you have to tighten that spacing way up, sometimes down to just 50 meters, so you can track those changing ground conditions really closely. And then you have these special cases, like huge solar power plants. Here, the strategy shifts again. It's really all about the massive area they cover. So the standard uses a density rule. 1 borehole for every 2 to 5 hectares. But, and this is super important, there's a non-negotiable minimum of 5 boreholes to make sure you have a good baseline understanding of the site. Okay, so we've pretty much mastered the XY plane. We know exactly where to put our drills. Now we have to pivot to that next critical question. Once we start drilling, when do we stop? How deep is deep enough?
And this is the core principle, the golden rule of this whole process. It's called the 10% isobar rule. An isobar is just a line of equal pressure. So the rule basically says we need to investigate down to the point where the new stress from our building, that's the pressure bulb you see pushing into the ground, is less than 10% of the natural stress that's already there. In other words, we only need to check out the part of the ground that's actually going to feel the weight of our new building.
So, that's the theory, which is pretty neat. But how does it actually work in the real world? Let's take a look at how this rule translates into some simple, practical guidelines for the most common types of foundations.
So for the most common kind of foundation, a simple shallow footing, the rule is really straightforward. You just take the width of the footing, we call it B, and you investigate to a depth of 2 to 3 times that width. That's it. It just makes sure you've explored that whole pressure zone for that specific foundation.
Now, when we switch to a big raft foundation,
That spreads the building's load over a much wider area, so the ratio changes. Because the stress isn't as concentrated, that pressure bulb is proportionally shallower. So for these big rafts, the investigation depth is usually just 1 to 2 times the raft's width.
Okay, now for deep foundations, like piles, which are designed to transfer loads way down to stronger soil layers. The rule is all about making sure you know what's below them. You have to investigate to a depth that is the greater of 2 options, either at least 5 meters below the tip of the pile or 5 times the diameter of the whole pile group. This makes sure the piles are actually resting on something solid and not just on a thin, strong layer with mushy stuff hiding right underneath.
But what happens when you finally hit rock? Well, you can't just stop and call it a day. This is a critical safety check. You have to drill at least 5 meters into the bedrock. Why? To prove that you've hit a solid, stable formation, and not just some massive, floating boulder that could shift or crack under the load. This is one of those non-negotiable rules that prevents absolute disaster.
Okay, so we've covered the where, that's our XY axis, and the how deep, our Z axis. Now let's bring it all together into a single, comprehensive framework that you can actually use.
And here it is, the investigator's matrix. This is your ultimate takeaway from all this. On the left side, you've got your location strategies for each type of project, and on the right, you have the depth rules that go with them. So, for example, if you've got a high-rise on a large site, you know you'll start with a grid pattern for location, and if you're using pile foundations, you'll use that 5-meter or 5D rule for depth. This one chart just pulls the entire standard into a clear, actionable guide.
You know, in the end, it all comes down to this one powerful idea from the standard itself. Every single rule we've talked about, from the spacing of boreholes to the depth of the drilling, is fundamentally about just one thing: managing the risk posed by the unknown ground right beneath our feet. So what does this kind of systematic approach to risk tell us about the future of engineering and design?